just the left-hand side? Can anyone help? Remember how we differentiate a square root? 1 over let me write the formula again right here. This is 1 over 2, the square root of the function times the function prime. Because that's how we differentiate the square root of x prime. Is 1 over 2 the square root of x. I should write times x prime, but there is no need because that's 1. So now, can anyone tell us how to start the left-hand side? What will you write on the left-hand side? You have to follow this pattern right here. So it's 1 over, yes, the square root of a squared minus b squared. So I have this and I have this, but now I'm here. Times what? Remember, a is the function because it's at the top, and b is the independent variable. So I have to differentiate a squared, but a is a function. What do I write? I'm differentiating x squared, and a is a function. How do I differentiate it? Yes, Tony, go ahead.
2a times dA over dB.
Excellent. Minus. I reached b squared, but b stands for x. So how do I differentiate x squared? In the same way I will differentiate b squared. What? 2b indeed. Equals. I finally reached the right-hand side, but this is a product. You can leave 4 outside if you don't want to mess with it just yet, and then we can distribute it later. So what do I have in parentheses? So a prime is 1, so it's, I'm sorry, a is the function, see? d over db times b plus a times 1. You can write it or not. Good, this is it for now. So what I'm going to do is I will have to distribute this quantity to these two terms and the 4 to these two. When I do that, the 2 will go away. See, when I distribute here, 2 will go away. When I distribute here, 2 will go away. So can anyone dictate the left-hand side after you distribute? So 2a divided by 2, so this is a over the square root of a squared minus b squared times dA over dB. And then I multiply this by this, and I get minus b over the square root of a squared minus b squared. I distribute 4 to b times this, so I have 4b dA over dB and plus 4a. So now, knowing that I'm after this, I will move this to this side and this to this side. Factor out dA over dB, and then divide at the end. So I have a over the square root of a squared minus b squared minus 4b. Minus has to be right here next to the fraction line. dA over dB equals 4a plus b over the square root of a squared minus b squared. So therefore dA over dB will be 4a plus b over the square root divided by a over the square root and minus 4b. It is recommended to combine, like find the least common denominator and eliminate the denominator because they are the same. You can say I'm multiplying the top by the square root and multiplying the bottom by the square root. If that's what you want to think in terms of that, that's fine too. So 4a the square root of a minus a squared minus b squared plus b over a minus 4b the square root of a squared minus b squared. I just wanted to mention the trig functions and the derivatives of 3 of them that we need to remember. If the other ones come into play, I will give you the formula. But 3 of those have to be remembered, because then we'll have difficulties when we integrate. So inverse trig functions. And this has to go. It's not working anymore. Okay. So we know arc sine x, also denoted by sine inverse x. We know arc cosine x, also known as cosine inverse x. Arc tangent as tangent inverse. Arc cotangent as cotangent inverse. Arc secant as secant inverse x, and arc cosecant as cosecant inverse x. I'm only interested in these 3 and their derivatives. Sine inverse x prime is 1 over the square root of 1 minus x squared. Cosine inverse x prime is the same thing with minus in front. And just one more. Tangent inverse x prime is 1 over 1 plus x squared. These you have to remember, please. And I would like us to practice. So these 2 are pretty similar, just minus in front. And this one has plus. These 2 have minus. This one has plus. Okay. And I would like to look here, problems 49 through 60, and choose a problem that has any of those 3 inverses, either sine inverse or cosine inverse. One more time, page 216. So problems 49 through 60 on page 216. So choose any problem you'd like to illustrate how sine inverse prime works, cosine inverse prime works, and tangent inverse prime works in any of those problems, and finding its derivative. Any preference?
Look at 57.
57?
Yeah.
Very good, very good. Let's look at 57. Good pick. In 57 we have y equals x sine inverse x plus the square root of 1 minus x squared. Good. So y prime. Can anyone dictate? Remember, this is a product, and remember this is a square root of a function, not of a variable. Square root of a function, so I have to use the quotient rule combined with the power rule. What will you tell me to write? Sine inverse plus x times Exactly. Exactly. 1 over the square root of 1 minus x squared plus. So I'm done with this. I had to use the product rule. The first function prime is 1 times the second function plus the first function times the second function prime. And now I reached this stage. How do I differentiate a square root of a function? 1 over, very good, to the square root of 1 minus x squared, but times, I would have stopped if 1 minus x squared would have been just x, but I cannot stop. I have to multiply by negative 2x. Excellent. Very good. Well done. Now I'm going to try to simplify it. Let's see if we can. Okay? So this is sine inverse x plus x over the square root of 1 minus x squared. I will simplify these two, and I have minus x over the square root of 1 minus x squared. What do we notice? We notice that those are the same, one positive, one negative. So the answer is sine inverse x. Okay. Let's choose one more. 59. Very good. 59 it is. 59, we have y equals arc cosine. Notice that they mean the same thing. We use two different notations. So arc cosine is the same with cosine inverse, and cosine inverse is the same with arc cosine. I prefer to write this when I type because I don't have to worry about power when I type it in the equation editor. So I prefer this notation versus this because of laziness, of course. So b plus a cosine x over a plus b cosine x. Good. So let's work on this for 1 minute. So we want y prime. Let me know if you need help. Does anyone remember when we talked about the tangent and the normal curve? What did we say? So if we have a function and if we have a tangent and the normal, yes, so the normal line and the tangent line at that particular point will be perpendicular. I just wanted to refresh your memory on that. Because now I realize that I did not put it on that handout on chapter 2. And I'm going to add it. Good. So when I differentiate cosine inverse or arc cosine, what do I have to write? Negative in front, 1 over the square root of 1 minus all this thing squared. Awful. But it doesn't even end there. Multiplied by what? What am I differentiating next? Yes, all this. I have to use the quotient rule. But a, b are constants now because there is x in there. Okay? So therefore, multiplied by quotient rule. The top prime. What is the top prime? This is 0. This is a constant. So then the top prime will be negative a sine x. Very good. Times the denominator. A plus b cosine x. Minus the numerator. B plus a cosine x. I have a fly in there. Times the bottom prime. This is 0, and this is negative b sine x. Negative b sine x. You already know I ran out of room. Over a plus b cosine x squared. Okay, let's try and simplify it a little bit. I should be squaring these, not the denominator, and try to make some sense of that. So the top will be squared, the bottom will be squared, but I'll keep it as a plus b. Oops. A plus b times cosine x squared. But then I have to change this into a plus b cosine squared over a plus b cosine squared. So I have a squared plus 2ab cosine x plus b squared cosine squared. But then minus b squared minus ab cosine x minus a squared cosine squared. There's not much hope other than the fact that I can, this is 2 of course. Not much hope other than simplifying these two. So this is just this part. Now I'm here, times negative a squared sine x, negative ab sine x cosine x. Now minus with minus, so then positive b squared sine x and positive ab sine x cosine x over all this thing, a plus b cosine x squared. A lot of work. As you see, yes, just these two go away. So it's negative. I can take the square root from this, and since it's a fraction, I can flip it. So a plus b cosine x divided by the square root I'm thinking that if I write a squared minus b squared plus, and even if I factor cosine squared, negative cosine squared. Oh, I can still simplify. Interesting. A squared minus b squared. Okay, let's see what we have here. What is left? Multiplied by negative sine x. Very interesting. Somebody thought about this. Okay, nice. So first of all, the negative with the negative will go away. One of these will go away. So then the top is sine x times a squared minus b squared. I should have put it reversed, and I'm going to. I'm going to erase the sign from the front. We don't like to put anything behind sine x, like anything behind the square root, because it may be confusing. It may get confusing. Okay, so now in the denominator, I have this, which is a plus b cosine x. But I could factor inside an a squared minus b squared, but then I have 1 minus cosine squared, which is sine squared. Very interesting. Very interesting. So then I simplify this and I get just a square root of a squared minus b squared over a plus b cosine x. Wow. After 3 pages of work, look, it's really simplified nicely. Which problem was that? Nice. 59. Very nice. A lot of work, however. Yes, I write big so you can see, but still it took me a long time. And a lot of factoring. Okay, I would like to, I still have a few minutes. I would like to talk about one more thing here that is mentioned in the problem. It's not mentioned in the text. I don't think I saw it anywhere. No, it's not. But it's right here in a problem, or actually in 4 problems. And it's a very important topic for physics. 2 curves are orthogonal if their tangent lines are perpendicular at each point of intersection. Show that the given families of curves are orthogonal trajectories of each other. That is, every curve in one family is orthogonal to every curve in the other family, and sketch both families of curves on the same axis. Let me explain this. This is a very interesting applications of differentiation rules. So let's say I have this curve, and let's say I have this curve. They do intersect only once. If I show that the tangent at this point of intersection to this curve is, if I show that, is perpendicular to the tangent at the same point of intersection, to the tangent, perpendicular to the tangent to the curve at the other point, at the other curve at that same point, then this function f1 and this function f2, they are called orthogonal trajectories. Now, how will I have families of curves? They will differ by a constant. So I could have these. One family looks like this, and the other family looks like this. If I show that every point of intersection, the tangent to this curve is perpendicular, not in my drawing as you see, is perpendicular to the tangent at that point on the red curve, then I will say the family of curves in red and the family of curves in green are orthogonal trajectories of each other. So let's pick a problem. Do I get to pick? I'll pick the first one. If you don't want to pick, I will. So x squared plus y squared equals r squared, and then ax plus by equals 0. Can anyone remind us what does the first equation represent? Do we remember? Yes, Thomas? Exactly. It's a circle of radius r with a center exactly where? At the origin. Very good. So if r is 1, this will be the circle. If r is 4, this will be the circle. If r is 9, this will be the circle. And you see it's a family of curves. For every r, I get a different circle. I picked integers that I could take the square root from, but it doesn't matter. They can be any r. What type of function is this? So the circle is not a function. The equation was the equation of a circle. What type of function is this? This is a function. Linear. So something like, for example, this is going to pass through the origin, I know, because this number is 0. As you see, at any point of intersection, but this is not the proof. We're going to have to do something else, right? So at every point of intersection, the tangents are perpendicular. So this family of curves and this family of curves are orthogonal trajectories. Okay. First step is I have to find the points of intersection. How do I find the points of intersection? I have to solve the system. How do I solve the system? This is quadratic. This is linear. What is my only option? Solve the linear for whatever you want. It doesn't matter. Excellent. I have to solve the linear equation for either x or y. It doesn't matter which one. Which one would you like to solve for? Good. So if I want to solve for x, I have to move by. It becomes negative and divide by a. So negative b over a times y. So I solved the second equation for x. Perfect. What do I do with it now? Exactly. Very good. I have to plug it back in. So this will be negative b over a y squared plus y squared equals r squared. So there is no calculus right now. All I'm trying to do is find the points of intersection between this family of curves and this family of curves. I graph them here. I know, but I really don't have these points. I have to determine them. Okay, so I continue. I have to square negative b over a y. What do I get when I do that? What do I get when I square this? Good. Very good. Perfect. Next step. Still algebra. No calculus yet. Yes, but I cannot.
So like you have to do.
Yes, I have to factor y squared. So I have b squared over a squared plus 1 equals r squared. So I'm solving for y squared. And I also find the least common denominator here. So r squared at the top, b squared plus a squared over a squared. Of course, I'm going to flip because there are too many fraction lines. So a squared r squared over a squared plus b squared. I'm almost there. I'm trying to solve for y. What should I do now to both sides? Take the square root. So I get y equals plus or minus ar over the square root of a squared plus b squared. So I found two different y values, but I have to find x as well. So I have x equals, when y is positive, then I have negative b over a times ar over the square root. And when y is negative, then I have b over a times ar over the square root. So now I have 2 points. Of course, I'm going to simplify. So I have 2 points. And you can say infinitely. Yes, but 2 different ones. Yes, I agree. But infinitely many. So can anyone give us those 2 points? When x is negative br over the square root of a squared plus b squared, how much is y? with the plus. So it's AR over the square root of A squared plus B squared. And the other option, BR over the square root of A squared plus B squared, and the other one with minus, negative yes. I thought I copied it incorrectly. I had to stop and look. Good. So we have 2 points. Fine. So all I did was to show that they intersect on this line, some in the first quadrant and some in the third quadrant. Okay. So now, what do I have to find next? I'm going to copy here the system. I need it one more time. It was x squared plus y squared equals r squared, and the other one was ax plus by equals 0, right? Yes. So what do I do next? Do I still have time? Yes. 8 minutes. So I found that these two curves intersect in these infinitely many points, one on one side, one on the other. Now, I'm talking about tangents. So what do I have to do? Where y is a function of x. X is the independent variable. So let's differentiate the first function, the first curve. It's not a function. 2x plus 2y times dy over dx equals 0. R is a constant. So therefore, I divide both sides by 2 and move 2x to the other side. So dy over dx equals negative x over y. This is coming from the first one, first curve. I repeat for the second curve. I get a plus b dy over dx equals 0. So then dy over dx is negative a over b, which is expected because it's a constant. This is a linear function. The derivative has to be a constant. So this is coming from the second one. Good. So I have the derivatives for both. I have the points of the intersection. What do I do now? I plug this point in here. There is nothing I can plug in here. I plug this point in here. What should the answer be if those two are orthogonal trajectories? What should I get in here? Exactly, I should get b over a. Then when I plug this point in here, what should I get? B over a. If that's the case, then I will say that everywhere these two meet, at each and every point of intersection, they have their tangents at that point perpendicular to each other. Therefore, the family of curves will be orthogonal trajectories, families of orthogonal trajectories. So let's just do that. So I have to divide this by this. Look, all this piece is the same. They will go away with minus in front. I will have negative b over a, right? It's x over y. Negative b over a with minus in front. Since these two are multiplicative inverses, negative multiplicative inverses of each other, b over a with negative a over b, then they are orthogonal at this point. When I create this, these two will go away because I will divide this by this. So I still have b over a in both cases. So therefore, the two families of curves are orthogonal trajectories because at every point of intersection, their tangents are perpendicular. I know I didn't get the chance to move on. So in the next section, I'm going to stop in a second. In the next section, we will investigate the derivatives of logs, all of them, and with x and with a function, and when the base is not e. And then we will talk about, this is another major topic, logarithmic differentiation. And we're going to talk about these two limits. In section 3.6, in section 3.7, if I find it. Yes, in section 3.7, we're going to look at applications in physics and applications in economics that use rate of change. 3.8 we do not do in this class because it's part of the previous one. Then we will move on to 3.9, which requires a lot of work. 3.9, a lot of work. And then 3.10, which is a long handout, but it's not a lot of work here. It's not. And then in 3.11, I will have a handout for you. We only look at the hyperbolic functions and their inverses, but again, we're only going to look at 3 of them. And that will be the end of the material for test 2. I am hoping to have at least 2 hours to review with you. I will bring the previous tests and we'll go over them in class. So, so on Monday, I'm hoping to accomplish 3.6, 3.7, and part of 3.9. Okay? If you have any questions, please stay. If not, thank you.